95% of all the reactions in organic chemistry, both 1 and 2, are called ionic reactions. Those are reactions where a nucleophile attacks an electrophile. So that's like all of the reactions that we've talked about up until this point. The other 5% are two types. The first type is the type that we're discussing in this chapter, radical reactions. And so we're covering that in Organic Chemistry 1. The second type you'll learn about in Organic Chemistry 2, and that's called paracyclic reactions. For now, we're not concerned with that. We'll come back to that, or you would come back to that in an Organic Chemistry 2 class. So let's talk about radical reactions and talk about how they're different from these ionic reactions. A lot of the exercises in this chapter are going to be drawing the mechanisms of these radical reactions. Remember, mechanisms are where you show how electrons move. You use curved arrows to show how electrons move to accomplish a transformation. Now, you've been drawing these curved arrows for a long time, and the heads of the curved arrows have been double barbed. So you have this two barbs on either side of the arrow. What you may not have realized is that that barb is meaningful. Each barb represents an electron that you're moving. So for example, if you have a curved arrow and you have not just one but two barbs, that means you're moving two electrons, the two electrons on your nucleophile. With radicals, remember a radical is a molecule that has an unpaired electron. So that unpaired electron all by itself will be adding onto things. And so the arrow is not going to be double barbed, it's going to be single barbed. You'll have a curved arrow, but the head will only have one of the two possible barbs on it. And that one barb is communicating the fact that you're just moving one electron. That's the first thing to note. That's the first thing that's going to be different in these radical reaction mechanisms, that you have these single barbed arrows. Now, they look kind of like fishhooks, especially when they're curved. So maybe if I put it the other way, have it like this, you can sort of see how it would look a little bit like a fishhook. And so they're called fishhook arrows. These single barbed arrows are called fishhook arrows. So when you draw the mechanisms for radical reactions, you use these fish-hooked arrows. You do not use the double-barbed arrows. The other big difference between radical reactions and ionic reactions is, in the case of ionic reactions, the curved arrows point at electrophiles, which are often atoms. In the case of radical reactions, these will form bonds. When you form a new bond, the curved arrows point to the space between the two atoms that are forming the new bond. I think this will be clearer as we apply it to specific reactions, so let's do that in exercise 11.7. To make this a little bit clearer, I'm going to draw out, I'm going to erase this, they have this HPR. I'm going to just draw that with the bond drawn out explicitly. Okay. Now if we look at what happens, you see that the bromine becomes a radical. Notice that unpaired electron there. That bromine becomes a radical in this process. And the radical that is on the carbon chain isn't there anymore. And what you see is a new bond to the hydrogen. So the hydrogen and this radical form a new bond. Now when you show a radical moving, you're going to use those fishhook arrows. There's only one electron here. So we're going to draw a fishhook arrow, and the arrow will not point at this atom. Whenever you form a new bond with radicals, the fishhook arrow points to the space between the atoms, the space where the new bond is forming. So notice I have this fishhook arrow pointing to the space where the new bond will be forming. So that's one electron, but in a bond you need two electrons. There are two electrons in that bond. The other electron is going to come from the bond between the hydrogen and the bromine. So one of those electrons moves. Notice I use the fishhook arrow. So the curved arrow is a fishhook arrow. And also notice that it's not pointing at an atom. Because it's creating a new bond, it's pointing at the space where the new bond is forming. Now that explains what happens to one of these electrons in this bond. But there are two electrons in that bond. So we have to show where that other electron goes. The original bromine has 3 lone pairs, and when you compare it to the final bromine, the 3 lone pairs are still there. You just have a radical in addition to those. And that unpaired electron comes from the second electron in that bond. The other electron goes back onto the bromine with a fishhook arrow. So those are the 3 fishhook arrows that will accomplish that transformation. You'll notice that this bond here is the bond formed by these 2 fishhook arrows, and this radical is the electron formed in that fishhook arrow. So this should look a little bit weird in terms of mechanism. It's definitely different from what we've done so far. But hopefully with a little more practice, it'll become more intuitive. Let's try another one. So in B, we see that bromine is our radical. It's very reactive. That's going to react with something. And in the product, we see that it forms a new bond. In addition to that, we see that the pi bond breaks. Okay, well, we know that the bromine is going to attach to this carbon here. It forms a new bond. When radicals form new bonds, you use fishhook arrows that don't point at atoms. They point at the space between the 2 atoms where the bond is forming. So I'm going to start at that radical, and I'm going to use a fishhook arrow to point at the space between the bromine and the carbon where it's going to bond to. Now that's only 1 electron. To form a bond, to form this bond here, we need 2 electrons. So we need to get another electron, and we're going to get it from the pi bond. And the evidence here is that the pi bond breaks. The pi bond goes away. Now there are 2 electrons in this pi bond. We're going to use just one of them. One of them, we're going to use a curved arrow. It'll be a fishhook arrow. So with just a single barb. And this single barb means you're moving 1 electron from this bond to the space where the bond is forming. So notice you have one barb from one fishhook arrow, a second barb from the other fishhook arrow. That's the 2 electrons in this bond. Okay, well, this pi bond has 2 electrons in it, and we've only said what happens to one of them. And the product shows us what happens to the other. The second electron here goes onto this atom. Now notice you're not forming a new bond here. You're really just showing what happens to an electron in this bond. It goes onto this atom. When you form a new radical, that's the time where these curved arrows will point at an atom. So when you form a bond, it points to a space. When you form a radical, the fishhook arrow points to an atom. So these 2 curved arrows here make this bond. And this curved arrow creates that radical, these fishhook arrows. Okay, let's get a little more practice. So in this example, we have 2 radicals. We have a radical on the left, that unpaired electron, on the tertiary carbon, and then we have a radical on this methyl group. And what we see is that we have no radicals here. Instead, we have a methyl group that has added onto this tertiary carbon. So we can show these 2 radicals coming together. There's going to be a new bond in between them in that space. Whenever you form a new bond with radicals, you don't have the curved arrows pointing at atoms. You have it pointing at the space where the bond is forming. So I'm going to use a fishhook arrow from this radical to point at the space where the new bond will form, and a fishhook arrow from the other radical to point at that same space. So those are both pointing at the space where the new bond forms between that purple and green carbon. And so these 2 fishhook arrows are describing the creation of that bond there between the purple and the green carbon. Okay, let's try D. D is interesting. You see the pi bond stays the same, so we're not going to rip any electrons off of that in this exercise. Instead, what you see changes is that there's a hydrogen here. It's not drawn in explicitly, but we can draw it in so that we can think about it more clearly. There's a hydrogen there, and what ends up happening is that you form a radical there instead. It should make sense that you form a radical there. It's on an allylic position. It's one atom away from this pi bond, and so it can be stabilized through resonance. The other thing you'll notice changes is that you start with a bromine radical that's really reactive, and you end up with HBr. And if it helps, I'll just draw that out with the bond there. So you can see you form a bond between the hydrogen and the bromine. Okay. So we want to form a bond between the bromine and the hydrogen that gets ripped off the molecule and leaves behind the most stable possible radical, the allylic radical there. Anytime you use these, you form a new bond with a radical, you use two fishhook arrows pointing at the space between the two atoms that you're forming a bond between. So we're forming a bond between these two atoms. We'll have one fishhook arrow starting on the bromine, pointing to the space between the bromine and the hydrogen. And another fishhook arrow. This hydrogen only has the electrons in this bond. It's going to use one of those. We'll use a fishhook arrow to point between the space between the hydrogen and the bromine. And so these two fishhook arrows are representing this bond between the hydrogen and the bromine, the creation of that bond. Now the bond to this hydrogen has two electrons in it, and as you can see from this single barb on this fishhook arrow, we've only shown what happens to one of them. The other one snaps back onto this carbon to create this allylic radical. When you create a radical, that's where you use fishhook arrows. You point the fishhook arrows at the atom where you're creating the radical. So we'll use a fishhook arrow here to point at that allylic carbon. And so this curved arrow is showing the creation of that allylic radical. And so you can relate this to the exercise we did in the last video, where we were looking for the most vulnerable hydrogens. This hydrogen is the most vulnerable hydrogen on this molecule because when it gets ripped off by a radical, it leaves a radical behind, and that radical is on the most stable position, the allylic position. Okay, let's try this again. We'll do this with E. Now, E might be a little bit tricky to visualize at first, but I think it'll help if you number the carbons. So I'm going to number these from the left to right. 1, 2, 3, 4. 1, 2, 3, 4. 5, 6, 7. Oops. Okay. So what we find is that as you go from the left to the right here, you break the bond between carbon 4 and carbon 5. There's no longer a bond there. So this bond between carbon 4 and 5 is going to break. Where do those two electrons go? Well, what else changes? Between carbons 5 and 6, we have a pi bond, and we have a radical on carbon 6. This one electron can move onto this bond to create the pi bond. But this pi bond has two electrons in it. This is only one electron, so we need another electron. We will get that from the bond that breaks, the bond between carbons 4 and 5. So this one electron in the sigma bond can move over. Together, these two electrons can create this pi bond. There are two electrons in this sigma bond. We've only shown what happens to one of them. The other one goes onto carbon 4 to create the radical. So these two fishhook arrows show the creation of this pi bond between carbons 5 and 6. And this one fishhook arrow shows the creation of this radical on carbon number 4. Notice that when you create a bond, the fishhook arrows point to the space between the space where the bond is forming. They don't point at specific atoms. And when you form a radical, the curved arrow points at the fishhook arrow points at the atom where the radical is forming. Okay, let's try F. I think this is the last one for this exercise. After this, we'll move into full mechanisms after we have sort of mastered the skill of drawing these fishhook, or at least practiced this skill of drawing these fishhook arrows. So what we see is we have a peroxide. We have a bond between two oxygens. That's a lot of oxygens to have a bond. It's an unstable bond, the bond between two oxygens. It only takes a little heat or light to break that bond apart. But so here we are drawing these sort of stick figure fossilized compounds that seem static and dead. When you think about this molecule in reality, though, of course, all these bonds are twisting and turning. It exists in galactic-sized clouds, hundreds of trillions of other molecules of itself, all knocking into each other. The bonds themselves vibrate around 10 trillion times per second. So 1 second to us is like over 219,000 years for these bonds. They vibrate that many times. Around 10 trillion seconds is over 219,000 years. So as these vibrate, if you heat them up, they vibrate faster. Or if you shine light on them, light is waves of electricity, and those waves make those vibrate faster. So as they vibrate fast enough, the bond breaks. And where would these electrons prefer to go? The oxygen or the oxygen? Well, they prefer both equally. And so the bond breaks with fishhook arrows. You could see that if you compare the structure to what you have in the product. And notice you have two of these because these are symmetrical. But compare what I have circled on the left with what I have circled on the right. Notice this oxygen is getting one of the electrons in the bond, that radical there. And so you take this bond and you use fishhook arrows to show the two electrons in it, one going on each of the oxygens. And that will give you this molecule twice. Once on the left, and again on the right. That's what this 2 is saying, that you have two of these. Notice these are really the same, so you have two of them. And you'll notice they're both radicals. They both have those unpaired electrons, so they're really reactive. Okay, so we've drawn a whole bunch of mechanisms in this exercise that show how you can use these curved fishhook arrows to create bonds and to create radicals. The crucial difference between this and the ionic reactions, where you have the double barbed arrows, is that when you're forming a bond between radicals, the barbed arrows, the single barbed arrows, the fishhook arrows, point to the space where the bond is forming between the two atoms. And when you form radicals, the fishhook arrow points at the atom that the radical is forming on.